Aaron, it's still time to leave. He's coming for the 10th lecture. And this should give you an idea that it's time to go. Maybe we're still missing a few participants. Were there more people this morning? Should we? I see some holes here. Waiting. Toi, tu avais un voisin, Philippe, non? Bon. T'as été vilain. On va attendre 2 minutes. Okay, so I guess I'll start lecture 10 and last. So this equation is stats equation for Q-colored triangulations, with the main series being this G of xy. This K is the so-called kernel, and this is, sorry, the right-hand side shouldn't be equal to the kernel. The right-hand, what I call the right-hand side of the equation is this thing, okay? Sorry? Yeah, so it's properly colored triangulations. You have Q colors, or equivalently, you're counting triangulations of some K-gon weighted by their chromatic polynomial. So said in those terms, you can evaluate this at any value of Q, which needs not be an integer. Okay, so there we are. So we were trying to apply to this equation the same ideas that we've seen this morning for a simpler problem involving walks in a quadrant. And the first thing we did was to consider the two values of x that cancel this kernel. And for some appropriate choice of y, we had to write y as uz. Then both roots of the kernel, called x0 and x1, could be legally substituted for x in my functional equation. And so we had now 4 equations relating, well, the size variable, the 2 roots of the kernel, the series G evaluated at x0 and x1, and finally the variable y and the series G of 1 and y. And these 4 equations, you have 2 that tell you that the kernel is 0, and you have 2 that tell you that this right-hand side is 0. Okay? So by eliminating y and g of 1y, we get two polynomial equation relating, so the size variable, the two series, and the value of g at these 2 points. And we have our favorite questions. That was that's IDs. An invariant is a rational function or a rational expression in Z, X, and the main unknown series, taking the same value at x0 and x1. And this morning, our solution of the quadrant problem was based on this remarkable property that from these two polynomial equations, you can construct two invariants. So are there invariants in this case? Yes. And one of them exists for any Q. So that's a proposition. And it has a rather simple expression. Let us define I of x to be g of x0 minus x over 1 minus x plus 1 minus x over z squared x squared. This rational expression in x, z, and g is an invariant. So the proof is not difficult. I mean, you form these two expressions for x0 and x1. You want to say that their difference is 0, and that it belongs to this. So you quotient by the two polynomial relations that you have here. And so checking that something is an invariant is never a problem. The problem is how you construct it. And this one, I would say, comes in finite time by playing mostly with those four equations. It's not directly a byproduct of these two, as we had in the walk case. You have to combine all four. And a way to obtain it a posteriori is to observe that there's no Q in that. And so if you eliminate Q between these two equations, you get it. But why, I don't know. So obtained by eliminating Q between the two equations. But that's an observation, not a method for finding it. So these two. You get rid of the Q, and you get something that decouples into I of x0 equals I of x1. No. An invariant is just taking the same value at the two roots. Needs not be 0. Yeah, it just happens to, yeah, it just decouples like as I of x0 is equal to I of x1. Okay, so that's one. And so what Todd did was to construct a second invariant, but only for those very special values of Q that I've shown this morning. So that's one of his propositions. So if you take Q of the form 4 times cosine square of chi pi over m, and you should avoid the extreme values 0 and 4, then there is a second invariant. So I can give it to you. I can try to say how you get it. Well, I'll do both. So this invariant is expressed in terms of Tm, which is a Chebyshev polynomial. So this m is the same as this one. So for instance, when we had 3 colored triangulations, m was 6, so you have a T6. And the definition of this is that Tm of cos theta is cos of m theta. So that's first or second kind of Chebyshev, probably first kind. And so the invariant looks like this. You take Tm, you evaluate it at something, and then in order to make this, then we will multiply by something that is just a function of the first invariant, and is such also an invariant. So let's be brave. What is the something you put in there? You have the square root of q over 2. And then you have q minus 3 plus 4 minus q over x. So 1 over x is what I denote by x bar. And at the denominator, we have something that looks unpleasant because it's a square root. It's 1 plus z squared 4 minus q times I, the first invariant. Sorry? Q minus 3, sorry, so 3, that's a 3. So you could leave it like that. This is an invariant, but it may not be rational because of this square root. So you should remember that Tm has degree m as a polynomial. And in fact, it's even or odd, depending on whether m itself is even or odd. So when m is even, this is nice. This is a rational function as required by our definition. But when m is odd, you have this square root that is around. And so what we do is that, in fact, we multiply to make this a big polynomial. We multiply by the square root to the mth power. And then this is, in fact, a polynomial in Z I and X bar. That's the other invariant, which I will denote J of X. Okay, so the question is how can you get there? By playing with these two equations, or these four equations. Yeah, I can try to give you an idea. So one way of reaching that is to start from the two equations K okay, so that's the two kernel equations. And then, so if you look at the kernel, it involves this G of 1y, which you can easily express in terms of I. Sorry. Yeah, so that's another point. You also need, so that's a parenthesis. You also need to know the value of this first invariant at x0 and at x1. And both can be expressed in terms of y as y squared g of 1 y squared minus y minus 2z g of 1y z. Yeah, I'm not even convinced by what I wrote here, so I should probably forget about this because I think that something is strange here. Well, you can look at our paper with Olivier to see how you get there. There's a crucial lemma. Maybe I will state the lemma because it's neat. So you transform your equations, you play with them, and at some point, you get a polynomial that has a nice form. Yeah. Sorry? So afterwards, we'll derive from the existence of these two invariants, yes, an equation with a single catalytic variable. Is that your question? Yeah, yeah. So that's what comes next. It seems that I didn't even write this lemma here. I'm sorry for that. Okay, so we have a lemma that tells you that if you look at this polynomial, let's call it, I don't know, P of uv, which is u squared plus v squared minus q minus 2 uv minus 1. Okay. Then there exists a polynomial. Here it's a polynomial, not a rational function, j of u, such that P of u v divides the difference j of u minus j of v which means that if you take the two V's that cancel this, then J will be an invariant. And here comes an if and only if Q is of this form. So this you can find in my first paper with Olivier. We have 2 papers on this topic. So that's the one that came out on Archive in 2009. I'm not sure when it was published. So somehow you massage your 4 equations. You get to something like that with some U's and V's that are related to x0, x1. And you apply this to construct an invariant. OK, so maybe we'll look at some examples. Or maybe I will first state. So that's what happens when you play with your equations, essentially with the kernel equations. You will, I guess, eliminate this G. Well, I don't remember exactly. I thought you were just expressing G in terms of the first invariant and getting rid of Y, so that you would obtain an equation between x0, x1, and the invariant I, and G of x0, G of x1. And upon taking then some homographic transformations, you get this normal form. And so for this normal form, you are able to conclude precisely when an invariant exists, when a polynomial invariant exists. Yeah. Yeah, so we also give the value the smallest possible polynomial, which is a Chebyshev polynomial. And that's what we apply to get this. When I say we, because then we did it for the Potts model, for the full Todd polynomial. OK, so here we have the 2 ingredients. We have always one invariant for any Q, and for those special values of Q, we have a second, which is whatever it is. Then the next ingredient was this invariant lemma telling you that there are few invariants. And this will also be the case here. And that's not the worst part of the proof, but I won't prove it. So again, I can summarize this by saying that there are few invariants. And so in this case, what happens that J of x must be a polynomial in the other one, I of x, with coefficients depending on z. So now we have, say, real coefficients because of this Q that can take real values. OK, so what I suggest now in order to digest this is to take a few values of Q of this type and see what we have, including the trivial values. Q is 1 and Q is 2. What happens? So first, m is 3, k is 1. And this morning we saw that this means that q is 1. So we have a first invariant I, whose expression is independent of q. And then we have one invariant. So let me write, I find convenient to define this big I as 1 plus z squared 4 minus q I. Okay. And so this must be a polynomial in I or in the alternative value big I. Okay. Okay, so our equation tells us that I to the 3 halves times the third Chebyshev polynomial evaluated at square root of q. So then we have q minus 3 that's gone, and that's x bar over square root of I is a certain polynomial in the invariant. So let's say that T3 of what of A is some alpha A cubed plus beta A. It's an odd polynomial of degree 3. I don't know its value by heart. So what we are really writing here is that I 3 halves times alpha over 8 x bar cubed over I 3 halves plus beta so I multiply out so this thing, which is polynomial of degree 1 in I, Laurent polynomial in X, and you should remember that I is essentially this rational fraction. This thing should be a polynomial in I. And in fact, we can decide that this polynomial has to be of degree 1. So this morning, when we were playing with walks, we had powers of 1 over x, which we had to adjust in order to determine the degree of the polynomial. So we had one invariant with 1 over x squared, which had to be a polynomial in the other, which had only terms 1 over x. And using that, we could determine the degree. And so the same thing happens here if you look around the value 1. Okay, because this I, it has a simple pole at 1. And so if it has to be a polynomial in I, this polynomial has to be of degree 1 as well, so for the simple pole to match. And so this you can do for an arbitrary value of m. And so this helps you decide that the degree is m over 2 in general. Yeah? Sorry? Oh, you're right. You're right. Thank you. I skipped to 3. So my expression is not correct. The numerator here is not correct. I have minus 2 plus x bar times 3. Is that your question? Thank you. So you should report these all over the place. Thank you. No, they can't. That's the important point. So that's my J. That's the first invariant. And I say that it must be equal to some polynomial of degree 1 with these two series depending on T. So that's the strength. Otherwise, it's obvious that it's a polynomial in X and I. But the strength is that this series here depend on Z only. Okay, yeah? Sorry? A square root of I? Where are we? Yeah, that's also 1. I decided that we had... OK, so everything is incorrect. I think this maybe is correct by now. Sorry for that. OK, so what should we remember here? By looking at what happens when x goes to 1, you determine the degree of this polynomial. So that's also what we did this morning. We had something quadratic on the left-hand side, so we needed a polynomial of degree 2. And then, as we did this morning, by expanding what you have on the left-hand side near 1 and matching this, you can determine expressions for the CIs, or these unknown coefficients, possibly in terms of specializations of our series J. So this morning we had, for instance, G of not that occurred in these coefficients. So if you do that in this case and with the correct expression, you get indeed expressions for C0 and C1. And in fact, so by expanding at first order, that is, you look at the contribution of the pole in 1 over x minus 1, you get C1 is minus 3 halves. And then you get a half plus 27 over 2 z squared. And these are just explicit values. No unknown series occurs here. So now what you can do, you plug this back into what I call the invariant equation this equation 1. And now what you get is a polynomial equation in Z, X, and the G of X0. So there's no additional unknown series in this case. And in fact, this equation is very simple because its solution is this one, telling you that there's no way to color a triangulation with one color. Big deal. But at least it's correct. It gave you something that's true. So let's move to the next example, which is also not very interesting. So now Q is 2. So the invariant equation looks I squared times the fourth Chebyshev polynomial, evaluate it at 1 over square root 2. Then I should be careful, that's 1 plus 2x bar divided by square root of my invariant is some polynomial in I. And now this polynomial must have degree 2. Because here on the left, you can realize that you have a double pole at x equal 1. So here you must also have a double pole at x equal 1. And so, again, if you expand now this equation 2 near 1, you will identify these coefficients. So you get first C2, then C1, then C0. And again, they are just explicit polynomials. So if you plug back to 2, then you get a polynomial equation in Z, X, G of X naught is 0. And then in this case, this equation tells you, well, in 2 colors, there's one triangulation of a polygon which you can color, and it's this one. And that's the term, after all the changes that we've made, that corresponds to this very small map. So that's 2 not so interesting cases. So let me tell you what happens in the case of 3 colors. So M is 6, K is 1. Then the invariant equation reads, so now I've lost my invariant, but I know it by heart. Let's try. Okay, this is the J, the second invariant, which should be a polynomial in the first one, and in fact, a polynomial of degree 3. And so you again expand around x equal to 1, and you get that C3, C2, C1 as polynomials. So what I wrote, known. So polynomials in Z. And then for the first time, you get this C0 here must be equal to whatever. So you have a half. It's C0 over 27, which is a part that's explicit. 3Z squared. Then you have a Z4 over 2. And then comes specialization of your series. And if you go further, if M increases, you would get in those CIs derivatives of your series G with respect to X evaluated at 1, 0. And so the larger M is, the higher orders you get for the derivatives. Okay, so this is my equation number 3. And so if you plug back these expressions, 3 of them known, 1 of them involving this series, what you get is a polynomial equation in Z, X, the main series, and its specialization at 1. And for the first time in this series of examples, this is really an equation, a polynomial equation in one catalytic variable. Which is essentially the equation we wrote this morning for bipartite maps. It's exactly the same one, but this time we've derived it from the equation in 2 variables using the existence of 2 invariants and the invariant lemma. Yes? Sorry? You have more of these auxiliary series that depend on the size variable Z, but on nothing else. And you still have 1 catalytic variable, hence algebraicity, but more and more of these algebraic series. You may remember in the lecture on these equations, I was writing things like, say, G of X, and then you had some series, A1, A2, AK, and then the size variable and the catalytic variable. We were looking at such equations, and what increases is this number K. And so this would be, for instance, my AJ. And as M increases, you get more and more of these auxiliary series, which are essentially these coefficients. Okay, so we've recovered that for 3 colored triangulations, you do have an equation in 1 catalytic variable, which we already knew. And so in general, what happens is that so we have written that this invariant to the power of M over 2 times the Chebyshev polynomial evaluated at this point is a certain polynomial, say with coefficients CR in I for R ranging from 0 to M over 2. So again, the degree, so let me call this big C of I. So the degree of C is obtained by looking at the order of the pole at 1. And moreover, you can compute, as we did, a few of these polynomials are explicitly known, of this series are explicitly known. So it depends on the parity of n for when m is even, like, say, in this case, the highest three are what I call known. And, sorry, Cn minus 2. And Cn minus 3 involves the series we are after, so G of 1, 0. And in the odd case, we just know two of them. And the next one, Cn minus 2, involves G of 1, 0. So all this is obtained by expanding around 1, the invariant equation. Okay, so at this stage, I claim that we have reached, for the problem of color triangulations, the state where we were this morning for Crevera's walks. We've written an explicit equation in one catalytic variable x involving the main series, G of x, y, which is hidden in I, and a number of series that are my auxiliary series here that depend only on z. And maybe 2 or 3 of them, in fact, are really explicit. And so by applying the recipe, you can, for instance, try to solve small cases. But one difficulty is that I don't know how to solve this for a generic value of m. So I know that the solution is algebraic, but I cannot give a generic algebraic equation that would depend on m. It's possible that there is one. But so far it's not been expressed. But at least from this, we have algebraicity. So that was one intermediate reason algebraicity of, say, G of x1, G of x0. So that's one step. And so in our 2 papers with Olivier Bernardi, that's the first paper where we prove, so for the first problem, maps weighted by the Potts model or the third polynomial, that when Q is of this special form, you get an algebraic series. And there are mysteries with that because we sometimes get nice algebraic equations. So I'll show you one example. That at the moment we can only prove using this very heavy method, which is a bit disappointing or exciting depending on your viewpoint. So let me show you one example before we move to the next case. So let me remind you that if you count planar maps, uncolored, when Q is 1, then we could write the solution, the generating function, m of t, where t counts edges. We said that the solution was algebraic, and in fact, it can be written, well, in fact, if you introduce a generating function for binary trees, which is 1 plus 3t b squared, then m should be b minus b cubed, or something like that. And in any case, you have this rational parametrization in terms of b. So that was one way of writing the generating function for planar maps in terms of a series B counting some trees. And so now, if you apply this kind of scheme to properly three-colored planar maps, then instead of this B, you introduce a series A that also satisfies a not too ugly equation. So it's T times 1 plus 2A cubed over 1 minus 2A cubed. Okay, so this should count trees of some kind. And then the generating function of three-colored maps is some explicit rational function in A. So the first result is now well understood because you have some bijections with trees, which unfortunately I was not able to discuss at length, but at least I've shown you one with buds and leaves and whatnot. This one, the only proof is this kind of ugly, heavy thing that we did with Olivier. So there's no understanding at the moment why the generating function of properly three-colored maps should be an algebraic series with this rational parametrization, that is, trees lurking around. Sorry? Is there? Oh, it's not too big, and I don't give it because so it's canonical because we've got rid of t, but set. No. And the denominator is one of these two pieces. So there's nothing ugly. So at the moment, it's a very complicated proof for a result that's not too bad. OK, so that's algebraicity for some values of Q. And this is the first step in the solution. But now you may remember that we are aiming to differential equations, which will now be valid for any Q, not only those ones. So that's the second part of these two lectures, where I have to teach you how, starting from an equation with one catalytic variable, so far we've learned how to derive a polynomial equation, which was something very nice, and now we have to learn how you derive from such an equation a differential equation. And what I'll do is that, as for the first half of the proof, where I played with the quadrant walks, I will do that to give you a flavor of what's happening on the linear problem of quadrant walks. So there's an expression in French which is avoir le nez dans le guidon. So it refers to someone who rides a bike and is so focused on going further, he or she only sees the lenker, how do you call, say, the front wheel. And so that's how I feel with this method, because I'm just copying and saying with my words what Tut did. But my feeling is that I don't have a good understanding of that. And unfortunately, I will communicate you this feeling. OK, but at least we've been able to extend this to the full Potts model. So I had what, which section could that be? It could be a 4. So I want to write differential equations for Creveras walks. OK, so back to Creveras. We had an I and a J, 2 invariants. So let me write them down again and try to use the variable x rather than y. So one of them had a double pole. And the other had a simple pole and involved our main unknown series, counting walks, ending on the y-axis. And we had written that the one with the double pole was a quadratic polynomial in the one having a single pole. And the equation was something like that. So t j squared minus j minus 2 t squared q0, 0, my auxiliary series depending only on the size variable t. And that was supposed to be I, which is, I repeat, OK, so I said, OK, this is an equation with one catalytic variable, and we've learned how to solve this using the recipe or using the quadratic method. Now, what else can we do to get differential equations for this series? So we'll start as in the quadratic method. So I want to form a perfect square here. So maybe I'll multiply out by t, tj, aha, there's a y. You didn't stop me. OK, and then I have here the beginning of a perfect square, which is tj minus a half squared is equal to, I have a quarter plus 2t cubed q0, 0 plus the invariant and so there's a denominator in x squared. So this is 1 over x squared times, in fact, a discriminant with delta of x having degree 3. Sorry? 1/4. Thank you. So that's the very first step in this quadratic method. And then you may remember that the next argument in the quadratic method is to check that there exists a series how should I call it, big X in T that cancels Tj minus a half. So a specific value of the catalytic variable that will cancel this term. And then the conclusion was that this series must be a double root of the discriminant. So that's the quadratic method. Okay, so in other terms, you have this polynomial of degree 3, which contains one unknown series. You know that it has a double root as a polynomial in X, so its discriminant must be 0, and this gives you, or this gave you, your polynomial equation for Q00. So really, we were writing that delta of X has a double root big X, and then there was a polynomial here of degree 1. Okay? And that was the basis of the quadratic method. So certainly its derivative with respect to X still vanishes at big X. That's the property with having a double root, but you don't have the square. And here you have a polynomial of degree, so now it's 1, because the derivative has degree 2. And so you get the equation for Q00 by essentially saying that delta and delta prime have a common root. So now the trick used by Tut to get a differential equation on Q0 rather than a polynomial equation is to also differentiate this with respect to the size variable. I mean, at some point you have to do this if you want a differential equation in this variable. So if you differentiate with respect to t, well, given that you have a square here, you still have a polynomial in X. Now the degree can be 3, and it vanishes at big X. Sorry? No, it's the same notation, but it's not the same R. It's horrible. It's a polynomial of degree at most 2 in X, and whose coefficients are series in T. Okay, so this thing is the new ingredient that will take you to some differential system first and then to a differential equation. So what can we do with that? So maybe I write a lemma. And the lemma tells you that you have something that relates PQR and this something I should copy. Yeah? Sorry? In the last what? Sorry. Yeah? There is a what? Sorry? So there's a factor x minus x. X is a function of t, yeah, big X. So that's our root. It's in R. What I'm just saying is that this derivative, which is now a polynomial of degree probably still a 3 in X, still has big X as a root, considered as a polynomial in X, because it had a double root. So if you explicitly compute the derivative here, so you'll differentiate this, and there will be one factor x minus big X left. And when you differentiate this, there will be also another one. So certainly, I could express this R, or R bar, in terms of P and its derivative with respect to T. Yeah. So I'm leaving them formal. And so the lemma tells you that you have a very nice relation between these 3 polynomials in X and something that's very symmetric, in fact. So P is this one, a linear factor that is left once you've taken out the double root in your discriminant. Q is something similar for the derivative with respect to X, and R is the corresponding term for the derivative in T. And the proof of that is simple. So what do you do? So I want essentially to eliminate big X and also delta between these 3 equations. So what should I write? That delta X, so I don't denote the prime. This is for the prime, squared over delta. So this, taking the square here, you get rid of this term, and you're left with Q squared over P. And if you do the same for the T derivative, you get that delta T squared over delta is R squared over P. And this one, you differentiate with respect to T. This one, you differentiate with respect to X. And you take 2 expressions, blah 1 and blah 2. Having done that. But then if you look, well, maybe I should tell you what are blah 1 and blah 2 without doing explicitly the computation. So what you have here is the same thing. Okay, but then when you're brave and you actually compute this derivative, so you get a double derivative delta xt, which you'll get also here. And in fact, the ratio of these two terms that you obtained is simply delta prime x or delta prime t. And this is q over r. You really take this expression, or multiply by x squared, and you differentiate it with respect to t. So this will give you a 2tx. And here, what will appear is the derivative of q naught naught with respect to the size variable t, the length variable t. Oh no, they are independent variables. Okay, and that's exactly this equation that we've reached here. So I repeat, we've got rid of big X in two different ways by taking those ratios. We've differentiated on the left with respect to t, on the right with respect to x. We got two big things, the ratio of which is just this term, and this is q over r by factorizations there. And so this gives you exactly this. So what are we going to do with that? So there's a smell of differential equations. It's even worse. There's a smell of PDEs because you have derivative with respect to x and with respect to t. But what I want to tell you is that the derivative with respect to x shouldn't be taken too seriously, and you have not complained here, even though I have t and t. So what did I say? That this one is differentiated with respect to x. So now if I write p of x as p naught plus x p1, where p naught, p1 depend on t only. And then similarly for q, so we said that q has degree 1 and r has degree 2. What I claim is that the above PDE in this lemma is just a compact way of writing a system of differential equations on these pi, qi, or I. So let's see. So let me write this down. The lemma is a system of ordinary differential equations relating the series pi, qi, or I. And by ordinary, I mean in T. Yeah, but I that's the R bar. All over the place, it's R bar.
It's also a bar there.
Yeah, yeah. somehow we'll never get back. We'll get back to Q00, but you won't see R anymore. Sorry for that. There's not enough letters in the alphabet sometimes. Okay, so why should this be true? So let me compute this derivative. So I have 1 over Q. Then I take Q squared over P. I differentiate this with respect to T. So that's 2Q QT P minus Q squared PT over P squared is equal to something similar with R and the other derivative. So here I've just differentiated those ratios. So there's nice simplifications by Q here, by R here. So, and I can multiply out as well by P squared. So this tells me that 2 QT P minus Q PT is equal to 2 RX P minus R PX. Okay, so we are not there yet. I've just converted something that was a PDE into another PDE. But now we should remember that these PQR, they are polynomials in X. So this, the whole thing here, is a polynomial in X. Of what degree? So QT should have degree 1 in X. P has degree 1, Q has degree 1, PT 1 as well. R is the big one, but when you differentiate it with respect to X, the degree decreases to 1. And R is 2, but PX has degree 0. So each of these 4 products is a polynomial, a quadratic polynomial in X. So this polynomial, or the difference between these 2 polynomials being 0, this means that each of the 3 coefficients, that is the coefficient of x squared, has to be 0, the coefficient of x, and the constant coefficient. So let me extract the coefficient of x squared. I get a 2 for sure, and then I want the leading coefficients in all pieces. So QT, its leading coefficient is Q1 prime, and this means the derivative with respect to the only variable that you have in Q1, so that's T. And then you have P1 minus Q1 P1 prime is equal to 2. So you take R, you differentiate with respect to X. So this term becomes 2XR2. So you have another 2R2 times P1 minus R2 up P1. Okay. So this is my equation, and I've extracted from it the coefficient of x2, and what it gives me here is polynomial differential equation between the pi's, qi's, and ri's. And if I extract x, I will get a second one. And if I extract the constant term, I will get a third one. Okay, so you're going to tell me that I have 3 differential equations relating many series. 1, 2, 3, 4, 5, 6, 7, 7 series in T. That's a lot. And that's true. And in addition, when you have differential equations, you also need initial conditions in T to determine completely the solutions. But the first coefficients we always know. I mean, you can compute inductively, so this will not be a problem. So I certainly need to do 2 things. I need to complete this system so that it completely determines all series, all the 7 series, and complete it in a, well, with more differential equations or with more polynomial equations. And I need to relate it to Q00, which is the series which I want to prove is differentially algebraic. So there's one step that I want to detail. Complete the system. And so what happens, unfortunately, I've erased that. So we had delta was x minus x squared p, and delta x was x minus x q. So one thing that you can do is, in fact, what we started from. So delta over p is delta x squared over q squared. And so q squared delta is p delta x squared. So this delta has degree 3, q has degree 1. So you have here 2 times delta x 2 times 2. Okay, so you have 2 polynomials of degree 5, and you know the coefficient of x3 in delta, which was minus t squared, maybe. Yeah. Yes, that's the only series. And somehow I've been brutal by introducing many, many unknown series. And the idea is that they must be related just because you know many coefficients in delta. There's just one unknown coefficient in delta, which is Q00. Well, it's a bit all over the place because you factored by this x minus x. So if you would match this with the expression plus delta 1x plus delta 2x squared plus delta 3x cubed, and then the Q00, it is in this coefficient here. You would get a system with a mixture of big X, the PIs, and Q00. But somehow what I'm doing here is really saying, come on, you've introduced all these unknown series, but you don't need that many. Because given that you know a lot about the coefficients of delta, they have to be related. So here, I'm writing one way to relate them. So I've got rid of X by by taking the square of this identity. And so if I now extract the coefficient of x5 in this identity, I get that q squared, sorry, q1 squared times the dominant coefficient in delta, delta 3, which is explicit, is equal to P1 times the coefficient of x2, so it must be 3 delta 3 squared or whatever. So you can get more identities between the PIs, QIs, or Is by putting the fact that in fact you know many coefficients of delta. So this is one step, the completion of the system with the information you get from delta. And the final thing you want to do, well, which is about of the same nature, is to keep this equation here, is to relate this to Q00. But this is again a coefficient extraction. Maybe it's not that interesting. That I didn't do it in my notes. How embarrassing. No, it's done. OK. So this is just going further here. So we have extracted the dominant coefficient from this identity. If you go one step further, you get a polynomial equation between Q00 and P1 and Q1, and there's also Q0 and P0. So this is a way of relating your unknown series, the one you're really interested in, Q00, that counts walks, to these PIs, QIs, or Is. But I think the main point on this example is the form of this equation, which we will get again in the triangulation problem. So I come to the last part, which is a number 5. Yeah. Variables, which ones? Yeah. I add many more. This is just an example. I can add more. Just the right number, so that the system becomes determined. And I also need some things like, say, PI at 0. But anything that is in the vicinity of t equals 0, you can compute, because it's just, if you start from the functional equation, it's just counting walks of small length. And so this you have access to that. Yeah, so I'm not doing those steps, but by eliminating in this system of 3 differential equations plus 4 more relations between PIs and QIs, plus the relation between Q00 and the PIs and QIs and or Is, you have 8 unknowns, 8 equations, some differential, some polynomial, and So I don't want to do that. It's ugly, and especially we know that the solution is algebraic. But that's the idea that we now want to convert to colored triangulations. So really the main ingredient is this, and you should remember that you knew a few more equations to complete your system. In this example, it's not so convincing because you have just one unknown series, but in this case, you will essentially have m over 2 unknown series. You will get a system of the right size and to which, well, I'm getting too fast. Okay, so getting back to triangulations. So this is our invariant equation involving a number of unknown series, depending only on the size variable now z, which grows with m, about m over 2 of them. And so what happens is that something like the delta that we had in this case, which had one double root, something will have, roughly speaking, this number of double roots. So you will have a polynomial with essentially m over 2 unknown coefficients, the counterparts of Q00. And for this polynomial, you are able to say that it has essentially m over 2 double roots. So having one double root in a polynomial forces one algebraic relation between its coefficients, namely the discriminant is 0. Having two double roots forces a second algebraic equation between the coefficients. And having m over 2 roots forces double roots forces a system of m over 2 relations between the coefficients. So here the counterpart of this delta having a double root is that if you define, so still delta of, say, u, which is this polynomial minus u to the m, again, there are many unknown coefficients in there, and it has essentially m over 2, so I guess it's m over 3 minus 2 double roots. I will call this number L, and I will call the roots U1, U2, UL. And in fact, for each of these roots, so they are double roots. So you have, so C is U I to the M, and you also have so for those UIs, you have U, C prime U is equal to 2U is M C evaluated at UI, and C prime Z is 0. I can tell you where this comes from. Okay, so where do these things come from? Just from basic trigonometry, essentially. So we want c squared to be c squared of u, or of I in our case, to be I to the m. So really, what we are looking at is that this Chebyshev polynomial should take the value plus or minus 1. And the other conditions here come from a related property, namely that the derivative of the Chebyshev polynomial at this specific point will vanish. So what you really have to prove is that there exists values of x such that t prime m evaluated at the big thing q, 3 minus q, q minus 3, q minus 3. So the roots of Tm prime we know, so this must be of the form, what is it, cosine j pi over m, where j, yes, thank you. So where, j is between 0 and m probably. So we know that the roots of the derivative of the Chebyshev polynomial. So what we want is to convince ourselves that there are values of x such that this big term takes this value. And then the value of the invariant evaluated there satisfies, well, that c squared of I at this point is I at this point to the m. So, sorry, the reason for that is that Tm evaluated at this point, this is minus 1 to the j. Okay, so for these points, you have the derivative that is 0, and the polynomial itself is plus or minus 1. And so the polynomial being plus or minus 1, combined with the invariant equation, gives you that C2 is I to the m. So this means that our delta at this point is 0. And the other two equations also follow by differentiation. Okay, so this proposition is, in the case of colored triangulations, the counterpart of delta has a double root that we had in the case of walks. And now there's the question of exploiting this to obtain something like that. And that's the next proposition, which is proved in essentially the same way. So we know that c of u squared minus u to the m has those essentially m over 2 double roots, which I've called ui, from I from 1 to L. And then you can check that what's left is a polynomial of degree 3. And then you have 2, or I prefer to write it with a factor over 2, u c prime u of u minus m over 2 c of u still cancels at all these series ui, but now they are simple roots, and you have a Q of u which has, I don't remember which degree, something small. And then the final equation tells you that this other polynomial So here I have just written, in terms of factorization of polynomials, these properties. So C prime Z factors vanishes at ui, u C prime u minus m C over 2 as well, and delta as well, except that delta has a double root. And so from this thing, in a way that's completely similar to what we derived here, you can derive that, that's a corollary, so there's some u's around, but otherwise it's the same equation. And the same calculation, essentially. So maybe I should insist on the fact that this L, the number of double roots that we know we have in delta, coincides with the number of unknown series CR. If you note that 3 of them are known in one case and 2 of them are known in the other. So we really have the right number of additional informations coming from the existence of double roots. And then the next steps, well, you need to complete. So this is, again, a system of ordinary differential equations in the coefficients of QPR. And there's maybe, again, 7 of them in this case. I've forgotten about the degrees here and there. So complete with a few polynomial equations between Pi, Qi, and Ri. You want a few initial conditions at z equals 0, as always with the differential equations. And you want to relate the main unknown series. So this is G of 1, 0. To P, Q, and R. Oh, look at that. And this you can do. And now you obtain a big system of equations. Most of them are differential equations, come from this compact way of writing a system, a few more initial conditions. And by doing some differential elimination, you get, for this one, the differential equation obtained by Tutt for Q-colored triangulations. So maybe one should conclude, because this is just for those special values of Q. But that's the easy part. So the system you can partially integrate. And so at the end, you get this equation that I wrote this morning. after some steps, you get the differential equation for g of the size variable evaluated at 1, 0, which counts by finite faces, Q colored triangulations. Of a diagon. Well, for Q equal to 4 cos squared pi pi over m. And so at the moment, this differential equation only holds for those values of Q. But if you think maybe of the, or maybe take the corresponding recurrence relation on the coefficients of this series, which is also something I wrote, and actually a very nice recurrence relation. And you inject the fact that these coefficients, they are polynomials in Q, and they satisfy a certain recurrence for all these values of Q's, then this has to hold for any Q. Somehow we have far too much information here. We have a dense collection of points in a segment. And that's the end of that's proof. Yep. Sorry? It involves Q, but in a uniform way. So that's the one. Okay, you were not here this morning. I can write it again. That's my favorite equation. It's nice anyhow. It's becoming messy. So if I state it in terms of C2 of T, the series, sorry, if I count things by vertices instead, where W counts all vertices, then the equation reads 2Q squared 1 minus Q times the variable W that now records vertices plus QW plus 10 times H minus 6W H prime times H dash dash, nonlinear term, plus the term that vanishes at 4, minus 20H minus 18 WH prime plus 9W squared, and this is 0. So maybe I should complete my answer. So this holds for those special values of Q. This is equivalent to a certain recurrence relation, which involves Q, but in a uniform way. And then you complete this with the polynomiality of the coefficients to say that it has to hold for any Q. Okay? Sorry? Oh, for any Q, for Q, a parameter, a variable. You had a question? No? Okay, so that's stat proofs, and I will finish with some final comments, which have to be final. Some very final comments, yeah? That's an excellent question. So this has been partially solved and partially guessed, and I'm partially working on it. Okay, so what is known? There is a paper by Onlisco and Richmond. Not much after Todd's results, so in the 80s, which establishes a map-like behavior for large values of Q. So behavior in rho to the minus n and minus 5 halves for large values of Q. So it's not an interval. They are missing some part. So maybe it's Q at least 5 or Q in some interval that is 3 point something. Sorry, 3 point something English notation, up to 4 maybe, or something like that. So they have a little window between 4 and 5, or 4 and something that they do not reach, where it is still believed that you have a map-like behavior. Now, what happens for smaller values of Q is more interesting. I need to blow my nose, sorry. So for Q small, so first what happens is that this series no longer has positive coefficients, because the chromatic polynomial, it will cancel at 1, it will cancel at 2, it will cancel at 0. So you have sign phenomena. So the critical exponent is conjectured using kpz for the very small values of Q. So if you write it in general, 4 cos squared of pi over some p, p needs not be an integer, then the coefficient is in n to some gamma, and I don't remember, gamma is a simple fraction in P. I could probably remember some values. So when Q is 0, we are counting certain types of trees, and then the exponent is minus 3. When Q is 1, so we get 0, but if we divide by Q minus 1, we're counting, I think, those bipolar orientations, and then we get minus 4. So we know a few values that confirm the kpz prediction. So if I plot Q here, so for Q 4, 5, and larger, the exponent is map-like, and then what happens is that you have apparently some QC. So here you have, I don't remember how it behaves, a kpz prediction, and you also have one very irregular point here, which is one of these Todd-Behar values. And starting from that, you have the 5/2 behavior. And no one knows what happens at this point. So you have something KPZ-like. Here you have a point that is, in fact, seems to be an accumulation point of zeros of those coefficients. And then you have the map-like behavior. Knižník-Poliakov-Samologikov, so that's some equations that relate critical exponents for planar maps to critical exponents for the corresponding models on the two-dimensional regular lattices. And so here we are looking at essentially the Potts model, or some specialization on the Potts model, and on the regular, on the square lattice, for instance, the exponents are known or predicted, whatever. And so this KPZ formula, as far as I understand it, and I don't understand it much, predicts the coefficient on random lattices, that is on maps, from the coefficients on regular lattices, like the square lattice. Sorry? So if P is large, so this gets to 0 and you get to 4. But apparently the KPZ prediction fails earlier. So this is a prediction, I would say, this explicit value of the exponent, which I was, so what I did, I took here and there some values of Q of the Tut-Behar form, for which the series is algebraic. I computed the corresponding algebraic equation using this recipe and studied the asymptotics and could check that indeed the exponent is what it was predicted to be. So I get up to m equal to 10 or something like that, something quite big. So that's one final comment, the asymptotics. So this is a big proof. There are better derivations when Q is 2. So the Ising model, as I said, the series is algebraic, and this is understood in terms of trees or mobiles, and you have several proofs of that. So 2 colors is better known, and there's still some ongoing work on the question by Lin Chao. Where are you? Lin Chao, and then Laurent and Marie. So 2 colors is fine, but if you want to play with 3 colors and with the algebraic equations I've shown earlier, please help yourself. So we have established for this problem and others nonlinear differential equations. You could still wonder whether maybe there exist linear differential equations. And this is not the case because for some specific subcases, you can find some asymptotic behavior that is not compatible with the existence of a linear differential equation. So for instance, for maps, so here they are 4 valent, that is every vertex has degree 4, maps with a spanning forest, so that's a special case. So in the Tut polynomial, that's doing mu equal to 1, and then you have a weight say mu minus 1 per component of the forest, per connected component of the forest. So in some ranges, when mu is between 0 and 1, we get an asymptotic behavior in N3, and then you have logs at the denominator, and this is not compatible with satisfying a linear differential equation. So that's a joint work with Julien Courtiel. And so this tells you that you need to be in this large class of series, those that satisfy nonlinear differential equations. And my last word will deal with universality. So we've established these results for general maps and for triangulations, for the general Potts model or for the Todd polynomial in both cases. And we have this intermediate result saying for all Qs of this form, then the series is algebraic. And I now think that for quadrangulations, for instance, for 3 colored quadrangulations, they are not algebraic. And the exponents are more of this type, I think, probably with n squared here or whatever. So 3 colors, they are nice for all maps, for triangulations, but apparently I doubt they are nice for quadrangulations. So I have no real understanding of what universality tells you, but one should be careful with that. Okay, and I stop here. Thank you.